come to my office after this, you can pick up a hard copy of it. So what did we do last time? So yesterday, so we introduced it last week. We looked at the dihedral group of symmetries of the triangle. And yesterday, we looked at the formal definition of a group. So a group is a set with a binary operation on it, satisfying these four properties. And these four properties are minimal in the sense that they're satisfied by a huge range of different groups in different areas of maths, a huge range of different binary operations and different sets. You're already familiar with lots of examples of these. Addition, multiplication of numbers, different various types of numbers, addition of vectors, addition and multiplication of matrices. Under various constraints, under various conditions, these kind of sets of certain matrices, etc., these kind of sets form groups with various binary operations. Now, we looked at these axioms yesterday, and we kind of described that abstract group theory is, in one sentence, just the study of what the consequences of these axioms are. What can you discover about the possibilities for groups, about the possibilities of the different kinds of groups there are, what kind of structure they have, and what kind of facts you can deduce about them based on these axioms and other properties, if you like. And we worked through a few of these immediate consequences yesterday. We learned that the identity element in a group is unique. There's only one and only one identity element. That element inverses are also unique. Every element just has a single inverse in a group. You can't have two distinct inverses. And, you know, from the existence of inverses, we get the cancellation law holds, theorem 5.3. And there's a couple of other theorems there. Theorem 5.4 about, well, this is something you're already familiar with. You know that if you want to take the inverse of a product of two matrices, from your linear algebra, you should know that the inverse of a product of matrices, well, if it has an inverse, it's going to be equal to the product of the individual inverse matrices, but in the opposite order. Everybody should have that kind of as a mantra. The inverse of a product of matrices is the product of the inverses, but in the opposite order. Inverse of A times B, the inverse of the matrix A times B, well, if it exists, so these are matrices here, if it exists, it's going to be the product of the individual inverse matrices, but crucially in the opposite order. Now, it turns out that this isn't just some special behavior that matrices exhibit. This is an instance in matrices of the general group theoretic fact that in any group, the inverse of the product of two elements can be expressed as the product of the inverses, but in the opposite order. So the inverse of A star B is equal to B inverse star A inverse. So this property you're familiar with from multiplication of matrices isn't just some weird special thing about matrices. It's an expression of this general fact that holds in every group. Now the bit about multiplying the inverses in the opposite order to how you multiply the original elements, that's crucial if you're in a non-commutative group, if you're in a group where the operation isn't commutative. If the operation is commutative, for instance, and some kind of addition of numbers, normal numbers, or multiplication of normal numbers, then you don't have to, you can forget about this changing order effect because it doesn't matter if you change the order, if the operation is commutative. But for operations like matrix multiplication, which you know isn't commutative, if you're multiplying two matrices, two square matrices, in general, you'll get different answers if you stick them in the opposite order. For operations that aren't commutative, it's crucial that you recognize and appreciate this fact that the order changes. Okay. Then a last theorem for now, which we're just stating, which we aren't going to prove. So it's actually kind of a It's kind of a technical induction type proof. But one of the group axioms is, of course, the associative axiom. If you're multiplying three elements in sequence, where is it there? Axiom 2, an A times a B times a C. There's two different ways to evaluate that, because you've only got a binary operation that multiplies things in pairs. So you can first multiply B times C on the left, as indicated on the left-hand side by the brackets there. Or you can first multiply A times B, as indicated by the brackets on the right-hand side. The associative property says that those two ways will always give you the same answer for the triple product A times B times C. Well, that's associativity on products of three elements. So theorem 5.5 says, well, as long as you've got associativity on products of three elements, it actually follows that you have associativity on products of any number of elements. So any number of elements written down a big long product in a row, if you're talking about a binary operation, it doesn't matter how you evaluate it. You'll always get the same answer, as long as you're talking about the same sequence of elements in the same order as you read from left to right. But how you choose to evaluate it, by multiplying pairs together and then multiplying the results by the other elements and so on, whichever way you arrange your brackets will always give you the same answer. Okay? It's not an extra axiom, it's a consequence of the single associative axiom. Okay? Now, we're not going to look at the proof of it, but you can prove it using just a careful induction type argument. Now, as the number of elements in the product increases, the number of different ways of bracketing it up into pairs increases as well. So, I mean, I can't even remember the total number of ways. There'll be some kind of combinatorical formula that will tell you the total number of ways of bracketing up the expression into binary operation pairs. But like, for instance, for a product of 10 elements, I'm sure there's probably hundreds of ways of doing it. So you need a careful induction argument to prove that they all give the same answer, based on the fact that you've got associativity on products of three elements. Okay. Now, for today's lecture, okay, so that was a quick review. That's longer than I wanted of what we did yesterday. For the rest of today, I want to focus on particular groups. Okay, so these are the modular arithmetic groups. So these are introduced in section 5.4 there. Now we've got two operations, addition and multiplication modulo n. Okay, so n is some fixed modulus. So that example there was matrices. For the modular arithmetic groups, we have two operations, addition modulo n, and multiplication modulo n. So these are two examples of binary operations. So n is some fixed modulus. So it's just an integer greater than 1. It's called a modulus. So what does addition modulo n mean? What does multiplication modulo n? Well, so you might be familiar with this idea already, but to add two numbers under addition modulo n, to add an a and b, well, you just add a and b in the normal way, add the integers a and b, but then the answer to the addition is not the normal sum a plus b necessarily, but the small remainder c that's left after you divide a plus b by n. Okay? So you take your two integers, a plus a and b, you add them, but then you divide that sum by n as much as you can, and that will leave a small remainder. Now that small remainder, it's the smallest positive remainder that you can have after dividing by n. So it'll be bigger than or equal to 0, but strictly less than n. Okay? Multiplication modulo n is just exactly the same thing, but using the operation of multiplication. So to multiply a and b modulo n, you look at the normal product a times b, the normal product of the two integers, but then you extract out of that the remainder c that's left after you divide a times b by n. Okay? So that leads to, for any particular modulus n, it gives us two groups. Okay? So it's the group under addition, So we get the group Zn plus under addition, where Zn is the set of all the possible remainders you can have. Now, all the possible remainders modulo n you can have, well, there's n of them. So there's n different possible C's that are possible to come out. Remainder of 0, remainder of 1, etc., up to a remainder of n minus 1. So the group is formed by all these possible remainders and under the operation of addition modulo n. The second group is Zn under the operation of multiplication. But for this one, as we'll discover, we need to get rid of some elements, perhaps. Remember, to be a group, you have to have inverses. Now, the identity element for the operation of multiplication is going to be the integer 1, going to be the remainder 1. So you multiply anything by 1, it doesn't change. But it will turn out that not every number less than n has a multiplicative inverse under multiplication modulo n. Only certain of them have. Now, this is something we explore fully in the second year unit, number theory and cryptography. But in definition 7.5 there, this shows the relevant one. So we don't necessarily consider the set of all the remainders. We just consider those integers a between 1 and n such that a is coprime to n. So coprime, we explained yesterday, coprime is a relation between a pair of integers. Two integers are coprime to one another if they don't share any common factor, any common integer factor apart from 1. Every integer can be divided evenly by 1. But if that's the only positive integer that divides both of the numbers, then we say that they're coprime. And in order to have an inverse under the operation of multiplication modulo n, the number you're talking about must be coprime to n. Now, we looked at some examples of that yesterday in the examples preceding definition 5.5. So let's look at what some of these sets for the multiplicative groups are. And then we'll investigate some of their multiplication tables, some of their Cayley tables. So for instance, so this is example 5.4. If you're looking at the group of multiplication modulo 4, the elements in the group there are only going to be 1 and 3, okay? Because the option 2 and 4 are excluded because they're not coprime to 4. So the only numbers less than 4 that are coprime to 4 are 1 and 3. 2 is excluded because 2 is divisible by 2, and 4 is divisible by 2. So they're not coprime. 2 and 4 are not coprime to one another. Switch to green. Z5, well, which of the numbers between 1 and 5 are coprime to 5? Of course, 5 is a special number on its own in this regard. Why is 5 a special number? In regard to talking about the factors of it, things that divide it. It's a prime number, yeah? So even on its own, 5 only has 2 divisors, say, 2 small divisors, 1 and 5. No other number divides 5. It's a prime number. No other positive integer divides 5. So all of the numbers strictly less than 5 are going to be coprime to 5. Doesn't matter what factors they might have, they can't share any factor with 5 because 5 doesn't have any factors. It's prime. It only has the obvious factors 1 and 5, 1 in itself. So you get the idea. Z6, what are the elements of Z6 going to be? The elements for the multiplicative group under multiplication modulo 6. Shout them out, somebody. One is, sorry, yeah, go on. 1 and 4. Should we include 4? Are 4 and 6 co-prime? No, because they've got a common factor of 2. What? 1 and 5, yeah? The other options, 2, 3, and 4, each of them is excluded because each of them shares a common factor with 6 of either 2 or 3. So the only remainders that you get after dividing by 6, which are co-prime to 6, are 1 and 5. Z7? Well, Z7 is like Z5 in that 7 is prime. So everything less than it is going to be co-prime to it. So Z7 is going to have its kind of full complement. And Z8, well, 8 is 2 cubed, so the things you have to exclude are all the powers of 2, less than 8. So that will leave behind 1, 3, or anything which has a 2 in it. So just 1, 3, 5, and 7. 2, 4, and 6, and 8 itself, they're all excluded because they're not co-prime to 8. So you get the idea of the elements that you have that are going to form a group under multiplication modulo 8. Okay. So let's have a look at a couple of these. Well, let's investigate these groups. So as we showed you in the, as I showed you last week, when you're talking about small finite groups, a nice tool you have to look at the group, to look at what's going on in the group, is to draw its what's called the Cayley table. So the Cayley table is represented in abstract form there. It's so we did this last week for the dihedral group of symmetries of the triangle. It's in a very different setting. Symmetries of the plane under the operation of composition. Here, for instance, well, there's an example Z5. Well, let's do another one. Let's do Z5 plus. There's an example of Z4 plus in the book, but let's look at Z5 plus. The Cayley table for this so it's a table where you list the elements of the group as row and column headings for the table. And in the interior of the table, you put the result of the operation. Now, it's not so crucial with these groups because these groups under addition modulo n or multiplication modulo n, they're commutative. The operation is commutative. It doesn't make a difference whether you think of 2 plus 3 or 3 plus 2. The order doesn't matter. But in general, for a non-abelian group, and a group where the operation is not commutative, you need to settle on some convention about exactly what entry is going in the table. The convention is the entry you put in row GI and column GJ is GI on the left and GJ on the right. So the same convention you have for addressing entries in a matrix. The ij entry in a matrix is the entry in row I and column J. That's that same convention going on here. Of course, you can forget about it here because this operation is commutative, so the order doesn't matter. So the entry which goes in the middle is just the entry of the sum of the row and column labels. Now we're doing addition modulo 5 here. So we're adding these integers and looking at the remainder modulo 5. Now across in row 0, of course, you're adding 0 to everything. So it doesn't change the numbers. So that's not too hard to do. In row 1, you're adding 1 to each of the numbers. So you're increasing them by 1. And of course, when you add 1 to 4, you get 5. But we're not looking at the output 5. We're looking at its small remainder left after you divide it by 5. You divide 5 by 5, it goes in once, leaving a remainder of 0, of course. Okay, so 5 is congruent to, or equivalent to 0 modulo 5. Okay, you add, going across row 2, you're adding 2 to everything. So you're increasing everything by 2. And the answers come out like that. So this last 1 is there because 2 plus 4 is 6. And 6 is equivalent to 1 modulo 5. Now, you quickly spot what's going on here. And, you know, to tell the truth, it ain't that astonishing or interesting. You know, in each row, it just takes the elements from the previous row, shifted one click to the left, shifted cyclically one click to the left. So the ones that fall off the left appear at the end again. And that essentially is what every group, every one of these modular addition groups looks like. So an example in the notes of Z4 under addition pretty much is the same type of structure as this one over here. So 0, 1, 2, 3, 1, 2, 3, 0, 2, 3, 0, 1, 3, 0, 1, 2. The same thing going on. Okay. What's more interesting is when you start to look at some of the multiplicative groups. So there's Z5 and Z8. Let's do one of the other ones we had, Z7, say. Why do I keep switching my colors here? Z7, now we're looking at the multiplication. Now 7 is prime, so we've got all the numbers 1, 2, 3, 4, 5, 6. So all the possible remainders that are left after division by 7, except for the remainder 0. So we're talking about multiplication here. Okay? So we're multiplying these numbers, multiplying them under the operation of multiplication modulo 7. And this is going to reveal, you know, everything, all the possible operations that are going on inside the group. Now, clearly, when you multiply anything by 1, it doesn't change it. So the first row and first column in the table, you know, they're just copies of the row and column headings. So you can just put those down. But then you start to need to evaluate these things when you come to the other entries. So 2 times 2, well, 2 times 2 is 4, it's okay. 2 times 3 is 6. And what's 2 times 4? When we're talking about multiplication modulo 7, 2 times 4 is 8, so, but 8 leaves a remainder of 1. So 2 times 4 is 1 modulo 7. So you're seeing there that 2 and 4 are inverses of each other. 2 is the inverse of 4 and vice versa. 4 is the inverse of 2 under multiplication modulo 7. 2 times 5 is 10, which is 3. And there's an interesting fact about Cayley tables, which you could have noticed in all the Cayley tables we've seen up to now. In any Cayley table for a group, every row and column contains each and every element from the group once and only once. So as you run along a row in the interior of a table, you never see duplicate elements. That's a consequence of the cancellation law. Theorem, whatever it was, theorem 5.4, was it? 5.3? Theorem 5.3, the cancellation law. You never get the same answer out from 2 times something, you know, unless you're talking about the same other number. So even without calculating it, I know the only one missing here is 5 from the second row. So this has to be 5. And, well, just check. 2 times 6 is 12. Yeah, indeed, when you divide 12 by 7, you're left with a remainder of 5. Okay? So 2 times 6 is equivalent to 5 modulo 7. So let's go a bit quicker around the others. 3 times 2 is 6. 3 times 3 is 9, which is 2. 3 times 4 is 12, which is 5. 3 times 5 is 15, which is 1. And the only one we haven't seen yet is 4. 3 times 6 is 18, which leaves a remainder of 4 after you divide it by 7. Yeah. Now, actually, at this stage, you know, we're duplicating some of the operations we've already done. What's 4 times 2? Well, I can just look at what's 2 times 4. It's 1. 4 times 3, it's going to be the same as 3 times 4. It's 5. you know, get the idea. 4 times 4 is 16, which is 2. 4 times 5 is 20, which is 6. 4 times 6 is 24, which is 3. So in each row, you're seeing each of the 6 elements come up once and only once across each row. 10, which is 3. 5 times 3 is 15, which is 1. 5 times 4 is 20, which is 6. 5 times 5 is 25, which is 4. And 5 times 6 is 30, which is 2. No, but it's not the difference between 7 and 15. It's the difference between, when you divide 15 by 7, how many 7s can you take out of 15? You can take 2, and the remainder is the 1. So it's the remainder, the smallest positive remainder, that is the output from the operation. Yeah. So the group is the arithmetic of the remainders, if you like. The arithmetic of the remainders modulo 7. Yeah. All of the things I'm putting in the table here are elements of the group. So it's always going to be a number between 1 and 6 in this, when you're talking about multiplication modulo 7. And, you know, this last row, I can work it out, or I can just use this principle that every column contains each and every element once and only once. So the one missing here is 5, must be 5. The one missing here is 4. One missing there is 3. One missing there is 2. And the one missing there is 1. 6 times 6 is 36, which is 1 greater than 35, which is a multiple of 7. So 6 times 6 is equivalent to 1. So these are examples of Cayley tables. They're the operation tables for the groups. So, okay, any other queries or questions about those that you'd like to ask? Okay, so some other examples in the notes. Now the multiplicative ones, the structure in the multiplicative ones is more interesting. As I say, the additive ones, you know, all just exhibit this same kind of behavior, because it's just each row shifts to the left at each stage. But the multiplication ones have a much more interesting structure. And the properties of these multiplicative groups is very important in number theory. So in the second year number theory and cryptography course, a lot of the work is to do with studying what goes on in these groups and, you know, using the consequences of what goes on in these groups to talk about facts about prime numbers and so on. Okay. But some other group ideas we want to talk about are, well, we have this notion of a cyclic group. So first of all here, in definition 5.8, you know the way that when we're talking about the groups in abstract, it's traditional to use the asterisk or star symbol to represent the operation. Now that's not any particular operation, it's just standing in for an abstract binary operation. But it can break your heart sometimes writing out loads of stars all the time. So there's a much more efficient notation called a multiplicative notation. And that's when you just forget about writing the star. So if you want to talk about the product of two group elements, okay, so up to now we've been talking about the product of two abstract group elements, G and H is G star H. Well, why don't we just save ourselves some time and ink and just leave out the star? So you just write it multiplicatively, G times H, okay? But the understanding is that if you're talking about an abstract group, you don't necessarily mean multiplication of number type objects. You're just saying you're multiplying the group elements, just whatever the binary operation is. So in the same way then, you can make use of exponents. So I can talk about the group element g to the power of n. And what that means is g times g, or g star g, just n g's multiplied together using the binary operation. Now the typesetting went a bit wonky here. In a similar way, you can talk about negative exponents. So just a correction here for definition 5.8. This next line, it should be, I'm defining there what I mean by g to the power minus m. If m is bigger than 0, g to the power minus m refers to, well, the inverse element g itself raised to the power m. So g inverse star g inverse, whatever, you know, the appropriate number of times. So m copies of g inverse. So we can just discard the asterisk symbol and just write our group operations, the binary operation, just as if it were multiplication. And we can use the idea of exponents then as well to refer to repeated applications of the binary operation. Then using this idea then, we can define a special type of group. This special type of group is called a cyclic group. A group is cyclic if it has a special type of element, and this special type of element is called a generator. Okay? And the special job that a generator does is, as its name implies, it generates all the elements in the group under using whatever the group operation is. Okay? So the definition says a group G is cyclic if it has an element such that the group is equal to just the set of powers of G. G to the power n, where n is any integer. And we use this angle bracket notation. G is equal to, the group G is equal to the group element little g inside a pair of angle brackets. That refers to the fact that G is a cyclic group with generator little g. Now, in the special case of finite groups, for a finite group G, G is cyclic if there exists a special element in it, which is going to be the generator. Now, for finite groups, you only have to consider the positive powers of the elements. So for a finite group G, G is cyclic if there exists a special element in it such that that special element generates the group. Okay, so there's some element there, you consider all the powers of it, you get all the elements in the group. G is equal to the set of these elements. Now, where n is equal to the number of elements in G, or the order of G. So n is the number of elements in G. It's what we defined last time to be the order of G. Now, sometimes groups are cyclic, sometimes they're not. So some groups are cyclic, some groups are not. Groups that are cyclic are especially easy to understand, because really it just boils down to the behavior of a single element under all its powers. And you combine together powers just by adding the exponents. So cyclic groups are essentially equivalent to the additive group Zn under some appropriate value of n. So groups that are cyclic, because they're just represented as all the powers of a single element, and when you multiply together two different powers, all you're doing is adding the exponents. So cyclic groups are kind of nice and easy because they're just equivalent to additive modular arithmetic groups for some particular value of n. But sometimes these multiplicative modular groups turn out to be cyclic too. So let's investigate these examples that we have Cayley tables for and see if any of them are cyclic. So if we consider Z5 under multiplication modulo 5, well, I didn't talk through it, but there is its Cayley table in the notes at the top there. Is this a cyclic group? Is there some element in it which generates the whole group? Well, it's not going to be, 1 is not going to be a generator, because 1 only generates itself. 1 times 1 is 1. 1 times 1 times 1 times 1 is 1. By looking at powers of 1, you only just get 1. But if you look at what 2 generates, so what 2 generates is 2 to the power 0, 2 to the power 1, 2 squared, etc. All these powers of 2. Well, let's list them out. Well, 2 to the power 1, sorry, 2 to the power 0 is 1. 2 to the power 1 is 2. 2 squared is 4. Now 2 cubed is 8, but it's not 8, it's 3. Because we're talking about multiplication modulo 5. So 2 cubed is 5. 2 cubed is 8, which is congruent to 3. 2 cubed is 3. What's 2 to the power 4? 2 to the power 4 is 1, so you're back at the beginning of the list. What's 2 to the power 5? It's 2. Well, you see, we already know what 2 times any of these is. So 2 to the power 6 is 4. 2 to the power 7 is 3. And 2 to the power 8, we're back here at 1. So you notice there that it does indeed list out all the elements of Z5. So Z5 is cyclic. There is a special element, namely 2, which generates all the elements. Now notice that Z5 is also generated by 3. So 3 is also a generator. Is 4 a generator? Well, no, because what are the powers of 4? Well, 4 to the power 0 is 1. 4 to the power 1 is itself, 4. What's 4 squared? In this group, 4 squared is 1. 4 cubed is going to be 4 times 1 is 4. So 4 only generates the elements 1 and 4. It fails to generate the rest of the group. Okay? But Z5 is cyclic because it has these 2 generators. Now what about Z8? Is Z8 cyclic? Are there any generators for Z8 under multiplication modulo 8? Well, there's its Cayley table, the bottom of the screen. Now, there's something about the Cayley table that tells you, which you can see in the Cayley table, that tells you it ain't cyclic. And if you choose any element and test to see whether it's a generator, so take 3, but you see, you look at 3 squared is already back to 1. And the same with 5. If you look at 5 squared, you get back to 1 straight away. 7 squared is 1. So under multiplication modulo 8, every element is its own inverse. So that means that any element can only generate itself and the identity element 1. That's all you get when you look at powers of that element. If you look at all the powers of 5 in the group, multiplicative group Z8, you only ever generate 1 and 5. You miss out all the other elements. So no. No, it's not, since for every x in Z8, we see that x squared is equal to 1. Yeah? So you're only ever going to generate. So the set of elements generated by x, that's what we mean by this angle bracket x notation, is just going to be, the set of elements is just going to be 1 and x, which is never the same as Z8, because Z8 has 4 things in it. Everybody happy that Z5 is cyclic, but Z8 isn't? Yeah. And what about this one? We've looked at Z7. Now these things actually, just while we're at it, in general, these things are called cyclic subgroups. So although the whole group Z8 isn't cyclic, but it does have these smaller cyclic subgroups within it. So if you take any element from the group, look at the angle bracket x, by definition, earlier in the notes, that's the set of all powers of that element x. That's going to be a subgroup of the large group. It's a small group sitting within the larger containing group, just like you have vector subspaces of their containing vector spaces. Those are called cyclic subgroups. Z7, let's come back to Z7. There it is. There's the operation table, the Cayley table for it. Is that cyclic? Well, it's kind of hard to tell just by glancing at the table. So you have to start drilling down and testing some of the elements. Are any of the elements going to generate all the elements? Well, let's think of 2. 2 squared is 4. 2 cubed is going to be 2 times 4. But 2 cubed is 1 in this. So 2 only generates 1, 2, and 4. It just generates 3 elements. It only generates half the elements in the group. If you look at any higher powers of 2, you're just going to cycle through those elements. That's why these things are called cyclic. You're just going to cycle through that set of elements 1, 2, and 4, 1, 2, and 4, when you look at higher powers of 2. Let's try 3. 3 squared, 3 times 3 is 2. 3 cubed, which will be 3 times 3 squared. Well, we already know 3 squared is 2, so 3 cubed will be 3 times 2, which is 6. Okay, it's looking good. 3 to the power 4 will be 3 times 3 cubed. 3 cubed we already know is 6, so 3 to the power 4 will be 3 times 6, which is 4. It's a new element, again good. 3 times 4 gives you 5. 3 times 5 gives you 1. And you notice there we went through all of the elements of Z7. So in Z7, okay, 2 only generates 1, 2, and 4, which is not Z7. So 2 is not a generator, that's what we said. But 3, when you look at all the powers of 3, 3 to the power 0 is 1, 3 to the power 1 is 3, 3 squared is 2, 3 cubed is 6, 3 to the power 4 is 4, and 3 to the power 5 is 5, and that's it. 3 to the power 6 will be 3 times 5, which you notice is back to the 1. You've gone through all of the elements of Z7 there. So Z7 is cyclic. It'll have at least one other generator. If you think about it, in general, the set of elements generated by G will be the same as the set of elements generated by its inverse. It's a general fact in any group. And in Z7, in the group under multiplication, 3 inverse is equal to 5. So Z7 will be generated by 5 as well. You can test that out from the Cayley table. 5 squared is 4, 5 times 4 is 6, 5 times 6 is 2, 5 times 2 is 3, 5 times 3 is 1. So you go through all of the elements there, looking at powers of 5. 2 wasn't, so neither will 2 inverse be. 2 times 4 is 1. And is 6 going to be a generator? No. 6 is order 2. 6 only generates itself, 6, and the identity, because 6 is self-inverse. 6 times 6 is 1. So it only generates the 2 elements, 1 and 6. So Z7 just has those two generators, 3 and 5. Okay, so it is cyclic. So it's if you look at it just as a system of powers of 3, it behaves quite simply. It's just about adding exponents of 3. Really. Okay, so I suggest you investigate some other examples of these groups. So that's questions 1 and 2, the end of chapter exercises. Just have a look at some of these other groups. Primarily the multiplicative ones. The additive ones they all more or less have the same type of structure. So you can do that in the tutorials this week, and then we'll look at the permutation groups next week. It's the other main examples of groups we're going to look at.